We are going to begin section 4 by taking a look at our exponential graph again of y equals 2 to the x. And you can see all I did was take a t-chart and I plotted those points in red to the right. And that should be very familiar to us. Again, we know that it crosses at the point 0, 1. These are powers of 2, so 2 to the first is 2, 2 to the second is 4, etc. Now on the right-hand side, all I did was take those exact same points and flip them. So instead of negative 3 1/8, it would be 1/8 negative 3, and 1/4 negative 2, and 1/2 negative 1, and 1 0, 2 1, 4 2, and 8 3. And this time you'll notice that that graph is hugging the y-axis instead of the x-axis. But if you look, they are reflections of each other over this diagonal line, which is the line y equals x. Now, we flipped those points around. We graphed them. The first one is the graph of y equals 2 to the x, and the second one I don't have an equation for. Now, it's a function because it passes the vertical line test, so there must be an equation that I should be able to write. And that's what today is about, is how do you take the inverse of an exponential function? And an inverse is called a logarithm. So if we have a base exponential function of a base b raised to the y power is equal to x, I can rewrite it in logarithmic form by writing log base b of x is equal to y. And there's a couple things that I want you to note. B is the base of the exponent and it becomes the base of the logarithm. Y is the exponent. That is what follows the equal sign because that's what a logarithm does. It solves for an exponent. So if you can place those two pieces, then you can rewrite anything in logarithmic form if it starts as an exponent. So in this example, my base is 2 and the exponent is 3. So if I'm going to rewrite this in logarithmic form, I would write log base 2 of 8 is equal to 3. Let's just practice that for a minute before we move on to how you evaluate those. This would be log base 4 of 64 is equal to 3. Log base 5 of 25 is equal to 2. So all we are doing in this step is taking one form and rewriting it into another. Now let's go the opposite way. If you have an exponential or have it in logarithmic form and want it in exponential form, you need to think about your base being 2, and remember what follows the equal sign is your exponent. So this is written as 2 to the third power is equal to 8, which of course we know is true. Now one way that I write it to have people remember is I kind of do a circle. 2 to the third power is 8. 10 to the third power is 1,000. This has helped people remember the order. 4 to the negative fourth power, remember negative exponents make reciprocals, is 1 over 256. Now, if you want to evaluate something and actually figure out what is that number on your calculator has a log button. It's the LOG button. If we want to evaluate log base 16 of 4, I'm going to enter log 4 on the calculator and I'm going to divide it by log 16. So as I do that, I will hit log 4 and I'll close parentheses, divided by log 16 and I'll close parentheses, and I get 0.5. Now I want to think about what that means as we start this section out. This means 16 to the 0.5 power is equal to 4. Let's just test that on our calculator. 16 to the 0.5 power, yes, it's true, is equal to 4, so that does check out. If I want to evaluate log base 1/2 of 256, I'm going to take log of 256 and divide that by log of 1/2. Again, you'll go to your calculator, log 256 enclosed, divided by log of 0.5, close parentheses, and you get negative 8. Now again, we want to think at this point about what that means. That means 1/2 to the -8th power should be 256. I want to check that on the calculator and take 1/2 to the -8th power, and I get the 256. Now notice there's no base on this one. I kind of left it blank. This is called a common logarithm. A common logarithm has understood to have a base of 10, and 10 will not be written in there. That's what the button on your calculator is designed for. The log button is a common log, so all you have to enter is log of 100, and you will get 2. So log of 100 is equal to 2, and again, let's think about what this means. 10 to the second is equal to 100, and yep, that checks out. Graphs of logarithmic functions come from graphs of exponential functions. Remember I said 3 is the base, and so we want to start with the function y equals 3 to the x power and see what that graph looks like first. I'll take numbers like -1, 0, 1, 2, for example. 3 to the -1st power is 1/3. 3 to the 0 is 1. 3 to the 1st is 3. 3 to the 2nd is 9. All I want is a base of what this graph looks like. Again, this is an exponential growth graph, which we are used to at this point. It hugs the x-axis and comes up and grows with a growth rate of 3. Now what a logarithmic function does is exchange your x and your y around. So all it does is take those points and flip them. So the graph of y equals log base 3 of x takes the points that we just graphed and flips them to 1/3 -1, 1 0, 3 1, and 9 2. You'll see that that hugs the y-axis, is not supposed to touch it. I got a little bit close to it. And if you compare, that is a reflection along the diagonal line y equals x. So this is the graph of y equals log base 3 of x. You can graph any logarithmic function by starting with its exponential. So this is a base of 1/2. I am going to do a t-chart of y equals 1/2 to the x power. I'm going to do -2, -1, 0, and 1. 1/2 to the -2 is 4. 1/2 to the -1 is 2. And you can see my other values in here. So -2, 4, -1, 2, 0, 1, and 1, 1/2. This is an exponential decay graph. Again, it's coming down and it's hugging the x-axis. So this is 1/2 to the x power. If I want to graph the function of y equals log base 1/2 of x, I'm going to take the t-chart that I just made and I'm going to simply flip-flop those points. In an inverse, the domain and the range switch. So I graph the point for -2, 2 -1, 1 0, whoops, and this should be 1/2 1. You'll see it comes up and hugs the y-axis. Again, if you look, this is a reflection over the diagonal line y equals x. And again, the second graph that I just did is log base 1/2 of x. Now that takes us back to the very first graph that we did. When we flipped the points around and didn't have a name for it, we started with a power of 2, therefore its reflection or its inverse is the log base 2 of x. We're going to just describe the transformations that have taken place after identifying what the parent graph is. The parent graph basically is take everything else away. So the parent graph of this is log base 10 of x, or like we said, the 10 is not needed, so just log x. That's called the common log. Now the 3 means there is a vertical stretch of 3, and the +1 at the end means it has moved up 1. Our parent graph to this one is log base 1/4 of x. The 1/4 is needed. This is a vertical compression of 1/2. And since the -3 is in parentheses, it means it has moved right 3. In our last example, the parent graph is log base 3 of x. The 2 out front means there is a vertical stretch of 2, and the 2 in parentheses being subtracted means it is moving right 2.